All right, next couple units are on statistical inference. We are going to make educated guesses about the world using statistics. We're going to make conclusions about populations from sample data. Okay? Today, and this unit is all about confidence intervals. Confidence intervals. What is a confidence interval? Well, let's read this little paragraph here. It says, in the first week of November 2012, a national random telephone survey of 1,101 adults was conducted by Gallup to see which presidential candidate they planned to vote for. The survey indicated 46% planned to vote for Romney and 49% planned to vote for Obama. Each had a margin of error of 3%. This result is an example of a confidence interval. Confidence interval, CI for short, is going to be a sample proportion or a sample parameter, which we will call a p hat, sample proportion or parameter. It's a statistic, not a parameter. And we will add and subtract a margin of error.
What is like what's on the left side of that?
It's a P. This is a CI, confidence interval. Confidence interval. Okay. Now, here's a question. This is kind of the basis of this unit. I got a jar of beans here. Some light beans and some dark beans. I want to figure out what proportion of these beans are dark compared to light. Well, what can we do? What are some guesses? What do we think, Ms. Falco? What proportion of these beans are dark beans? 50%. 50%? What do you think, Ms. Adams?
55%.
You think it's a little bit more, 55? What do you think, Mr. Funk?
It's 48.
Maybe a little bit less. Don't go too crazy with these guesses here, guys. Ms. German, you think maybe a little less, a little more?
Like 62.
Wow. Great job. Way to go out on a limb. All right. Well, I don't know. Okay? I have no clue. I actually do know, but I'm going to pretend like I don't know. I have no clue. Somebody did. Not me. No clue how many dark beans there are or how many total beans are. I have no clue what the proportions. But yes, we could guess. Okay? That's one way to do it. Well, I don't have time in this class for us to be able to do our homework, to be able to count all these beans out, right?
Mm-hmm.
Okay, this is kind of an example of like polling. You know, we want to figure out who's going to win an election. The New Hampshire primaries were yesterday. We wanted to figure out who was going to win the nomination for New Hampshire for the Democrats and the Republicans. Well, they didn't ask everybody in New Hampshire, right? It's impossible to do that. Okay? Instead, to kind of predict the results, they polled, right? And they took a what? A sample of the population. Well, could we do that to figure out maybe a better guess than just a random guess for our beans? Maybe we could just take a handful out, Miss German.
Like that big of a handful?
I don't know. What do you think? What do we think? Should Miss German take just a little handful like this and say, okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 total beans. 1, 2, 3, 4, 5, 6, 7, 8, 9 of which are dark. Should I just say that we have 9 out of 17, or what does that equal to? We'll need a calculator today. It's close to 50. What is it? 0.529. Should we use that guy? Or what would produce a better statistic? Right. Just like how we'd want to do more trials for simulations, we would want a bigger sample to produce a better statistic. So, bigger sample gives us a better idea. So, Ms. German, you took a bigger sample than I did. What was your sample size? $30 dark beans.
There's this naked one. Or white one.
25 white ones.
So that's 30 out of 55. What do we get for that? 0.54. So maybe a little bit more than half. Now, if I took a larger sample size and counted this out, I'd probably have a better idea, okay? Well, that's valuable, sure. But what we're going to be doing today is we're going to say, hey, instead of just giving a value, let's not just give a value and say we think it's going to be around here. Let's not just say around 0.54, around 0.529. Instead, let's give a range of values, okay? We say instead of 0.54, maybe it's going to be between a low value and a high value based off of this, okay? And this is how we are going to take our sample proportion and add and subtract our margin of error. Now, in the previous problem, they just said add and subtract 3%. And if we add and subtract 3%, it would be 0.57 and 0.51. Well, that's a little bit too simple. And actually, the 3% is not just made up. This margin of error is not made up. There's going to be math involved to find margin of error. Okay? What we will do is we'll actually find the standard deviation of our sample data and multiply it by a z-score, which is standard deviation distance, so that we know how much to add and how much to subtract. Now, how are we going to find all this stuff? It's actually going to be very simple. There's a formula that we will follow, okay? That's the goal. We will produce this interval, and instead of saying, hey, around 54% of our beans are dark, we'll say, hey, I have a pretty good idea, pretty good chance that the percent is between these. So instead of saying, oh, it's going to be around here, I'll say, most likely it'll be between these two values, okay? That's the idea of a confidence interval. We will figure out kind of a low number and a high number, and we'll say, hey, I'm pretty confident that the actual proportion of beans in that jar that are dark is going to be between those two numbers, okay? Do we understand that? Does that make sense? Okay, good. Well, here's the formula that you need to know. Now, if I went through this example, we could just remind ourselves of some of these definitions of terms that we did back in like the Unit 1 and Unit 2, like our population. Here's our large container, 2 types of beans, light and dark. What proportion of the beans are dark? That's what we're trying to figure out. What is the population in this example? It doesn't have to do with people, right? Because we're talking about beans. It would be all the beans. Remember, the population is just the total or like all of whoever you are examining. Let's remember that definition of population. Everybody we are examining. The parameter of interest is what you are examining about your population. So, Mr. Englander, what's our parameter of interest in this situation? Yes, the percent of beans that are dark. Just by looking at the container of beans, we thought it was around 50%. We went through and we took a sample. We found it was about 52% using Ms. German. What was your samples? 54%. The proportion that she found that was from a sample, is that a statistic or a parameter? Remember, parameters tell us about populations. Statistics tell us about samples. So this is a stat. Statistics is samples. Statistics come from samples. Parameters come from populations. This is just kind of a review of terms that we will be using. Statistics and samples, parameters and populations. In this case, this 0.54 would be a statistic since it came from samples. Now, what was the sample size? This is what we will call N. Remember using the letter N for a sample size. This is not the amount of dark beans, rather this is the total amount of beans that we pulled out of the jar, or it's the total amount of people that were polled, or it's the total amount of trees that we looked at in a forest, okay? Ms. German, what was your sample size? 55 beans were pulled out. That is our sample size. So remember, N is our sample size. In this case, it was 55. This is the total amount, and you can just say surveyed. All of these terms we need to be reminded of for this unit. If everybody took a sample, would everybody obtain the same proportion? No. What we'll find out is that they're going to be normally distributed. We'll get to that later. Does it allow us to truly know the true proportion? No, but if we have a extended kind of range, we will be able to say that we are fairly confident that the actual proportion is going to be between two certain values. I kind of want to skip this, but we can do it. This is the parameter distribution, or the distribution, sampling distribution is what I want. Sampling distribution. Up P has the following properties. This isn't so important. Once we get to the confidence intervals, it's important, but it's okay. As long as the sample size is large enough, it is an approximately normal distribution. Well, this is talk about later. The mean of the sampling distribution is going to be equal to the population parameter. Not super important, but this is important. The standard deviation of our sample is going to be this. Now, it takes AP Calculus 2 tests to be able to get this. Okay? Here, I'm just going to tell you, this is how we are going to find our sample standard deviation. Okay? Now, why do we need a sample standard deviation? Well, we're not going to just make up values to add and subtract to our margin of error. We're not going to just make up 3%. Instead, we will use specific values that we will add and subtract based off of how confident we want to be about our range. We will take a z-score. A z-score is a standard score. It's our standard deviation distance. And we will multiply it by our sample standard deviation to find this margin of error. This will be just a mathematical way to figure out what we are adding to our statistic that we developed. Okay? Now this might seem crazy to you. I'll just tell you that when you flip over the page of your notes, here is your formula. Right here. This is how we will produce a confidence interval. We will add and subtract our z by our standard deviation. That will give us the range that we will add, or it's just the amount, the distance that we will add and subtract from our sample, and that will then give us our confidence interval. Okay? The margin of error, what we said here, the margin of error is everything that we are adding and subtracting to our sample statistic. If our margin of error was 3%, we'd add 3% to 5.4. We'd subtract 3% from 0.54. So in the formula, the margin of error is everything after the plus or minus. Remember what the p hat was. The p hat was our sample proportion. Okay, that's what Miss German found, this many dark beans out of this many total. Remember the n. The n is our sample size. It's not the amount of successes, it's just our sample size. The last thing that is important is this z value. They call it z star. Okay? Z star is the number of standard deviations away from the mean we are. We will use different z values depending on how large our confidence interval needs to be a certain level of confidence. Now, let's remember our standard deviations and our z values for a normal distribution. Let's remember our normal distribution. If I was at my mean, I was a z distance of 0 away. I could go out -1 and 1 standard deviations away from the mean. What percent of our total values were between -1 and 1 standard deviations away from our mean? 68%, exactly. Well, what we were going to do is, if we are asked to produce a 68% confidence interval, we're going to use the z of 1. Now, if I went 2 standard deviations away from my mean, what percentage of my data would be within that? Yeah, remember that's 95. Now, actually, that is more of an approximation than we would think. And what we would use here, if we were to produce a 95% confidence interval, we would use a z of about 2. However, more exact, that's not how you spell exact, we will use 1.96. Don't worry about the z values found at the bottom of the yellow chart. We will tell you the z values that you will use, okay? Well, let's go ahead and construct a, don't worry about the 80, let's use a 68 and a 95% confidence interval for the proportion of dark beans based on Miss German's sample proportion. Okay, so here's our formula for a confidence interval. We got the p, which is our sample proportion. The z comes from our percentage. Let's probably write that down. Z value is our percent confidence. If we want a 68% confidence value, confidence interval, we'll use a z of 1. If we want a 95% confidence interval, we're going to use a z of 1.96. Okay? Then everything else we plug in. We plug in P times 1 minus P divided by N, and we take the square root of that. We multiply that by P. That's our margin of error. We will add and subtract that from our starting to get that range. Okay? So let's do it for Miss German's data. We need first our P hat. What was your P hat? What was your sample proportion? 55.55. Good. What was the N? We'll need that. What was your sample size?
Oh wait, 55 was the sample size.
55 was the sample size. 54 was our percentage. Let's change that up. Okay, so 54 was our proportion, our sample proportion. 55 was our sample size. Now, if I want a 68% confidence interval, this will say use a Z of 1. Okay? All we need to do now is plug everything into our formula, calculate it using our calculator, and we will have a range, and we'll be able to interpret what that means. Okay? So let's do it. We will have 0.54, that's P, plus or minus my Z, which is 1 for a 68% confidence interval, times our standard deviation, which is this formula, the square root of P, times 1 minus P over N. Now, let's all have our calculators out. Let's all practice calculating this. Now, multiple ways to do this. I'd probably advise you to not do it all at once, but you will find that if you do it all at once, it actually isn't bad. If you have a newer operating system, you don't need as many parentheses as you think you would need. But we just need to calculate this. Now, don't worry about this plus or minus until the end. We'll worry about that at the end. Instead, let's just find out what this is. Now, it's going to be 1 times the square root of this. If you were going to do it step by step, this is what I would do. Take the 0.54, multiply it by the 1 minus the 0.54. Take that value, divide it by 55. Now I want to take the square root of that answer. If you have a new operating system, second square root, pop up, press enter, and that number goes underneath the square root. Okay? Now, since this is 1, it's not going to change it when I multiply it. There is my margin of error. It's 6.7%. So I got 0.54 plus or minus 0.0672. What I'll do is take that value, add it to 0.54. Gives me my high end. And I'll take that value and subtract it from 0.54. If you have the newer operating system, you could just subtract and pop up here. Press enter. Press enter again. And you get 0.4727. Now, if you wanted to do this all at once, you could do 1 times the square root. Turns out you don't need the parentheses. You can just do 0.54 times 1 minus 0.54. Close your parentheses for that. Divide that all by 55. It actually works out. You don't need that parenthesis there. And you get that value that we were looking for at 0.672. So that's done all at once. It's up to you whether you want to do it one step at a time or all at once. This is our confidence interval. Instead of saying around 54% of our beans are going to be dark, we say I am 68% confident that the actual proportion of beans in that jar is between this value and that value. Okay, so it's just a new way to saying things. Instead of saying it's going to be around, we could be a little bit more specific with a level of confidence using a z-value to figure out these standard deviations. I say there is we are 68% confident, 68% of the time that we do this using a sample, we're going to get between here and here. Okay? Now, if I did a 95% confidence interval, what is going to change? What's that, Ms. Rios? The z-score changes, okay? Let's do a 95% confidence interval. Everybody's going to do it on their own. I will come around and make sure we're all doing it. All that's going to change for a 95% confidence interval is the z-score you're going to use. You're going to use 1.96. So just expand things a little bit more. If you think about it, 68% confident, well, if I want to be more confident that our actual proportion is in this range, I'm going to make it a little bit wider. And if this became wider, then I could say, all right, I'm more confident with a wider interval that my actual proportion will lie in there. So go ahead and do the work using your calculator.
So can I just do it all big and then multiply it by 0.54 at the end?
Well, you'll add and subtract it from 0.54. Okay, so go. Fill out your formula. 0.54 plus or minus, the only thing that changes is 1.96. And let's see what we get. Can everybody also check your bags? We've had calculators walk out on us. Who's got one? Oh, who's got one of my calculators right now? 3, 4. Raise your hand. 5, 6. Really? One just popped up. Okay. Please look through your stuff if you perhaps took a calculator with you one day. Okay, check your answers with a neighbor. I'm coming around making sure everybody does it. All right. All right, we have the same answer. Okay, that would be your high end. Now find your low end. I got a different value for this. Double check now here, use Z. This should be 1 minus 0.54. That's not the Z value. It's always going to be 1 here.
Oh, I thought we were finding, that's my work for the 95%.
Right. And I'm saying this is correct. That's correct.
Oh,
this
that's
stays as 1. That's all.
Oh.
That's the low end, yep. Okay, now you're going to take the square root of that. Can you go up? Oh, no. Good. I'm glad you know that. Okay. I would advise you to do this one step at a time. That, then divide by that, then take the square root of that answer. Why are we getting that? 0.54, 55? Oh, okay, never mind. You're good. Now, what do we do with that value? So that's what's in here. You need to multiply that by 1.96. Perfect. Okay, that's our margin of error. That's what we add and subtract from that.
That number?
This number that you have right here, because it's the 1.96 times that. That is what you're adding and subtracting from that.
Okay.
Good. Now, it's not 0.54 times, it's 0.54 plus and minus. So you have to do this with a plus and this with a minus. If you have a newer operating system, it's pretty nice. You could actually write everything out, 0.54 plus, then everything, 1.96 times the square root of 0.54 times 1 minus 0.54. For some reason, because of the square root, you don't have to worry about this, an extra set of parentheses. And this is actually your high end that you should get. You can go up, select this thing again, move all the way to the left, and just change the plus with a minus. Now, like, make sure we're careful if we're doing all things at once. But if we have it correct, boom, you get your interval. Okay? Any questions? Anybody need help with these calculations? All right, so we got 0.408 and 0.6717. Now notice, this is larger than this up here. Does that make sense to you? Why, Miss Bushman? Yeah, because we have to be 95% confident. Well, we probably need a larger range to have more confidence. Now, this is pretty large, 0.40 to 0.67. Well, what could I do maybe so that I have a smaller range, but still have a 95% confidence? Put your phone away, Mr. Englander. This is an important question. What could I do with just anything that I did with finding our beans to make this a smaller range, but keep the z value the same as 1.96? How can I shrink the standard deviation, maybe? Mr. Englander? P, let's say the P stays the same.
Well, you have to make the whole thing bigger, right? And gain more.
There. So what is that? Not P, that's what? N. We need N to be bigger, right? Everybody, let's go back. What if Miss German changed her sample, and instead of picking out 55, she picked out 255, but she still got a sample of 0.54. If we do a 95% confidence interval, watch what happens. My high end becomes, what do we want? 555 beans? Sure. 555, 35,000, nope, 555. All of a sudden, we go to 0.58 instead of 0.60. 2% less. Significant? Yes, if you think about percentages. If we did this with a minus, instead of 55, we did 555. All of a sudden, the low end will shrink in the positive direction. And we go from 0.49 or 0.50 to 0.58. Okay? So this significantly shrinks. Sorry, I'm not even thinking about this. I went from here. This one. We went from 0.67 down to 0.58. We went from 0.40 to 0.49. If she actually did that, well then, boom, we have a smaller range. So the larger sample, the more confident we are that the sample will be closer to the actual parameter, which is the actual proportion, well, that means that the range that we will have is going to be smaller. Okay? So keep that in mind. Larger sample size, smaller interval. Okay, how do we interpret this? Well, this statement we will become very, very familiar with. We would say we are whatever percent confident that between whatever our values are of the whatever we're trying to study would do that. Okay, I would say we are 95% confident that the proportion of dark beans is between here and here. Now, turns out there are 2,255 total beans, 1,048 of which are dark. The actual percentage, 1,048 divided by 2,255, is 46. 46%. Well, 46 is in our interval, so it counts. 46 is actually outside of this interval. Shows you why a 68% confidence interval, valuable, but not as valuable as if we expanded it out and we were 95% confident by going 2 standard deviations away from our sample mean. Okay, that's confidence intervals.
You confuse me hard because you switched up the colors on the 68%. Now down here on the answers, you have the color switched.
Oh, you're right. Look at that. This should be green because it's a 95%, and this should be yellow.
Now you just got 2 yellow.
And now we can stop being haters. Great. Fantastic. I'm just kidding. That's not supposed to be like that at all. Okay. Here we go. Let's practice doing a confidence interval. Here we go. And then we'll start our homework. 5,000 American workers surveyed. 2,445 said they were satisfied with their job. We want a 95% confidence interval. All right, we need all these values. Let's write them down. We need p hat. It's our sample proportion. We need n, our sample size. We need z, the standard deviation that we will use for our confidence interval. Mr. Meyer, what should I use for n? There's 2 values up there, 5,000 and 2,445. Which one should I use?
2,445.
No, I should be using 5,000, which is my total sample size, which is why we use the 55, which is our total sample size. Make sure we write down that n is our sample size. Miss May, what about our sample proportion p hat? What did you get for that? So that would be, exactly, that is the correct amount of people that said they are satisfied, but we want a proportion. This should be a percent. Let's make sure we write up here that p hat is our proportion. It should be a percent. So we take 2,445, we divide it by 5,000. What do we get, Mr. Funk? 0.489. Ms. Simpson, what do we use for z? Exactly, because we're doing a 95% confidence interval, we're going to expand by 2 standard deviations, exactly 1.96. The 0.489 is the 2,445 that are satisfied divided by the total in our sample. Okay? Now that we have all this information down, we can use our formula to produce our confidence interval. Go. That looks good. Yep, that would be P. P times 1 minus P divided by N.
Are we gonna round?
The third decimal place is fine.
So that, it would be
Yep, that's the high.
1 minus 0.4.
No.
No? Do I go back to this?
Yep, 0.489 minus that, right? So it's plus or minus those values.
Well, I got negative 1.7. So negative 1.7.
No. Remember, this comes first, then plus the value. This comes first, then minus the value. So you got to do 0.489 minus that in that order.
Minus point.
That.
I got you.
Okay. Check. We're a little off. Put the low number before the high number, Ms. Burke. Good. Check your answers. Yeah.
Is it okay to get a negative number?
No, I shouldn't get a negative number. Let's see what happens.
No, I typed the whole thing in.
You need a parentheses in there. That's good.
I don't know why I got it.
It's okay. Take the square root of that number. Multiply it by 1.96. That's what you're looking for. So you're good. So add 4.489 plus that, 0.489 minus that.
That's only Oh,
This is off.
by what? How?
It's just off.
What?
What is going on? No, that's the wrong N. That's the wrong N. N is 5,000. Our total sample size is that. Good. Keep going. Yep, that's right. Yep. Good. And then just do the other one with a minus. Good. Okay, we get, what do we get? Don't forget to take the square roots of that number here. So at 2.2499 divided by 5,000, make sure you take the square root of that. Now multiply that by 1.96. That's your value for all of this that you add and subtract from 0.489. Okay, you should get 0.489 plus or minus what value?
0.0138.
That. Okay, if we did it all in one step, well, you should just get your answers. If you did it in multiple steps, you should get the plus or minus this. And make sure you do this in order. The 0.489 plus this value, that's your high. 0.489 minus the value, that's the low. And we got 0.475 and 0.503. That's just what I got when I plugged it into this. This is 1.96 root of 0.489 times 1 minus 0.489.
I thought you meant that you were putting it in instead of 1.96.
Oh, no. Okay. Now, this is very small, right? Compare this to our other 95% confidence interval that had a range of like 27%. Why is this so small? Exactly, because the N is super big. The larger our N, the shorter our confidence will be. We've got to be pretty confident that this sample is going to be close to the actual proportion of all Americans surveyed. Okay? What was the population that we are studying? American workers. That's what we're trying to figure out. American workers. And what is the parameter? The parameter is what we're studying about American workers. What are we studying about American workers, Mr. Johnson? Yeah, their satisfaction level. Okay. Let's do our homework. Get out a sheet of paper. All right, Tanya wants to figure out the proportion of seniors that are going to attend prom. Tanya interviewed 50 seniors. There's a total of 175 seniors at this school. Of the 50 that she interviewed, 36 plan on attending. Question A, what is the population that we are attempting to study? Question B is, what is the parameter that we are going to study? Question C is, what is our sample proportion? And question D is, create a 95% confidence interval. Don't start D until you do A, B, and C and we go over it.
You want us to write out all of this?
No, just the answers are fun. Tanya is trying to figure out the proportion of seniors that are going to attend prom. Tanya interviewed 50 seniors. There are a total of 175 seniors at the school. 36 of the 50 that she interviewed plan on attending. What is the population? What is the parameter? So population is the group of things, group of whatever. Parameter is what we are attempting to study from that group. And C is, what is the proportion, the sample proportion that we can find. Okay, discuss your answers with a neighbor quickly.
Can you refresh me on satisfaction level for the work?
Good. Nope. Right. It's of the people that she interviewed.
This be how I set it up? Okay. Just messing.
Yep. Okay. Question, Ms. Rios.
So the C hat,
Yep.
do we do 50 over 175 or 36 over 50?
It's a great question. Should I do 50 over the 175 or the 36 over the 1 over the 50, or should I do the 36 out of the 175? Right. The 36 out of the 50 is correct. Why? Because she only interviewed 50 seniors. That is going to be her sample size. That is N. Go ahead and write that down as well. That is our sample size. She interviewed 50, 36 plan on attending, 36 divided by 50. That is going to be our sample proportion. Our population is the seniors. What's the parameter that we are attempting to study? Yeah, the percent of which are going to the prom. All right, well, based off of this parameter, this sample proportion, and your N, and the fact that you're doing a 95% confidence interval, why don't you go ahead and create that confidence interval? Go. Check your answers again.
Rude.
Not rude.
Just something wrong.
That's wrong.
Okay, I was gonna ask you on that, but
It's our sample size.
yeah, but we used 5,000. So
That was our sample.
okay,
That's
whatever.
not all the American workers. Come on, do it. Hide your paper. Come on. Doesn't look right. The 0.172 is wrong. 36 out of 50 is 0.72. That's right. Good. 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 No. Where'd you get 0.68 from?
I don't know, I made that up.
How did you get that?
Just divided 36 by 50.
Did you?
Huh, apparently not.
Right. That's wrong. What's our N value? N is our total sample size. Think about what you're using. Yes. I'm using my sample for P hat. I need to use that sample size for N. Perfect. All right. Good. We should get between 0.595 and 0.844, right, Mr. Holtz? Right. Good. Where do people screw up? People screw up with the sample size, typically. People also screw up with the P hat. For some reason, 36 divided by 50, that's how we get our P hat. We use our sample for our sample proportion. We use our sample for our sample size. We didn't care that there's 175 seniors. Got that, Mr. Holt? Yeah. Okay. Next question. More than 95% of people surveyed say they wash their hands after they use the public restroom. Over 95% of people say that. What's a public restroom?
Oh, I did not.
Sorry. More than 95%. If I poll the class, I guarantee you, all of you are going to say, oh yeah, I wash my hands after I use a public restroom. But there were people that were sent out into major cities. They stood in bathrooms. They watched people either wash their hands or not wash their hands. I know. And turns out they found that 5,250 of a total of 7,836 actually did wash their hands. What is the population? And this is just Americans. Yep. What is the population? What is the parameter? What is the p-hat? And then do a 68% confidence interval.
Do we even need to pay attention to it? What is that?
We don't. It's just there to possibly trick you, but to kind of provide context to the problem. Yeah, round to the second decimal place is fine. Population, it'll just be Americans that use public restrooms. The parameter is the percent that wash their hands. How do we calculate p-hat, Ms. Pushman? Divide what? Exactly. Divide these two values. Now, what am I going to use for n? Do I use 5,250 or do I use 7,836? This man. Good. Now that we have that, what is my z value that I'm going to use because I'm producing a 68% confidence interval, Mr. Holtz? 1 is correct. 68%, remember from our notes. 1 standard deviation to the left and the right covers 68% of our normal distribution curve. So that's how much we're going to expand things by. Really? Yes, Ms. Van.
So if we're leaving this, it's gonna be on the slide, right, the rest of the.
We're going to just stop and say that you did your homework. Okay? Mr. Messner, thank you. Okay. I got 0.664 and 0.669.
Yeah, I got it.
You guys probably rounded. 0.665 and what?
0.675.
Yeah, that's fine. Okay. Notice very small. Why is it very small? Very large N. Very large N. Well, we got one more question we're going to do. Very simple. Last question. And we're just going to go straight to a 95% confidence interval. All right. 1,025 American women were polled. 482 said they don't get enough time for themselves. Produce a 95% confidence interval to show, and then answer, fill in that statement. If you produce a 95% confidence interval, what are you going to show? I just want you to do a 95% confidence interval, but I want you to tell me what you're showing when you produce a 95% confidence interval.
That was from the old one.
Do the new one.
Oh, I didn't. You normally are like, okay, now do the next.
Pretty much what it did. Should I go away again? Okay. What do we get for P hat, Miss Champagne? 0.47 is correct. What is the N, Miss Burke?
1025.
Yep. What is the Z that I'm using, Miss Bushman?
1.9.
Miss DeVries, did you get the range? Working on it. Miss Jameson, did you get the confidence interval? What? Did you get the confidence interval? What are your answers?
Oh, no, I just said
Mr. Holt, did you get the answers? What'd you get? 0.429? 0.439? Somebody else get 0.439? Okay, 0.439, and then 0.5? Sweet. What are we showing, Ms. German? Yeah, it's most likely we are 95% confident that the true proportion is between these two numbers, okay? Nope, I'll take it on Tuesday. That's the one thing you have to do. You have to hold on to this until next Wednesday. Oh my goodness. Put it away. Lock it. Range of values which, okay.
My name is Sam.
Yes. Let me get you a pass.
Can I get this one? Yeah. I'm for recovery.
Go ahead. Thank you. You guys.